Hello everybody. Today lecture will be on the capacitors. So we're going to delve into fascinating world of capacitors. So what exactly is a capacitor? Uh, in the realm of electronics, a capacitor is a fundamental component that stores electrical energy in an electric field. So capacitor does not dissipate any energy. Instead, capacitors store energy in a form of electric field. When we talk about the capacitor and the application that we can find, think of it as a temporary storage tank for electricity. When you connect a capacitor to a power source, it's charged up, storing energy. Once charged, it can release this stored energy when needed. This ability to store and release electrical energy makes capacitors versatile and essential in countless electronic devices. And as an example here, for one application, if you see, now you have the output of the outlet, which is AC, and then after rectification, you'll find that it has only the positive, not the negative cycles. And then after that, it need to be smooth. You know, this ripple in the output voltage, the varying DC, it's a varying DC. So how you get rid of this ripple? By adding capacitor. That's one of the application that you can find. Okay, so what are the components of capacitor? Well, now let's break it into a bit further. A capacitor consists of two conductive plates. We call it here electrode. Separated by an insulating material known as dielectric. You know, this one in the middle, like a sandwich. The one in the middle, that's insulator. Dielectric does not contact. But the outer plates or electrodes, they are made of conductive material. So the dielectric prevents direct contact between the plates while allowing the electric field to exist between them. The dielectric material used in capacitors influences the property of capacitor. When voltage is applied across capacitor plates, the dielectric material blocks the flow of current through the material. These are changes in the dielectric material at atomic level. This phenomena is called polarization. And this dielectric material could be made could be like Teflon, polypropylene, glass, titanium dioxide, mica. So there are many different materials used as dielectric material. Okay, so when we connect, let me make it bigger so you can see it. When we connect a capacitor to a voltage source, one plate becomes positively charged and the other becomes negatively charged. This potential difference across the plates creates an electric field, and the capacitor store energy in this field. So what is the definition of capacitance in this case? Capacitance is a measure of a capacitor's ability to store charge on its plates. In other words, its storage capacity. It's like you have a tank and you want to store water in it, but this tank does not store water, store charge. Charge. So that's the definition of the capacitor. And that's why there is a relationship, if you look at the equation we have here, that the capacitance, which is the capacitance of a capacitor, we'll give it letter C, uppercase C, that's the capacitance, is equal to the total charge, which Q, uppercase Q, that's the total charge, divided by V, which is the voltage difference between the two plates. So that will be the definition of the capacitance. What is the unit of capacitance? It's measured in farads and give it the letter F. And as we discussed in the beginning of the semester, the charge, the unit of charge, Coulomb, measured in Coulomb. And the voltage in V. So the relationship is C is equal Q over V. So 1 farad is equal 1 Coulomb divided by 1 volt. That will be the definition of the or the unit of measure applied to capacitor is the farad, letter F, uppercase F, named after the English scientist Michael Faraday, who did extensive research in this field. All right. All right. So let's now take an example about this formula. Okay. We'll take in this example, let's say that, but let's me first write the equation. C is equal Q over V, where C is the capacitance of a capacitor and Q is a charge, total charge in Coulomb, and this is the voltage. I will take a simple example. The first example is, let's say that the total charge that we have is equal to 1.32 millicoulomb. Okay, millicoulomb. That's coulomb, not capacitance. That's coulomb. When you put it in the behind the numerical values, it's unit. Not how you find C. But first we have to find the voltage. So let's say that the capacitor that we have, and we know that the capacitor is like two plates and there's dielectric between them. You can make air. Air is insulator. And then the voltage. Let's that you have voltage equal to 60 volts. And the charge on the capacitor, that's equal to 1.32 millicoulomb. So what is the capacitance, C, of this capacitor? So we'll say C is equal Q over V, and Q is equal 1.32 millicoulomb divided by 60 volt. That will be equal to 22 microfarad. What is micro? Okay, what is micro? Well, 1 microfarad, it's very small one. It's equal 10⁻⁶ farad. That's the how to convert the unit. So if you ask how we did this, found the 22 and you divide 1, okay. I'll make it now step by step to show. 1.32 millicoulomb divided by 60 volts. First, you're going to convert millicoulomb to coulomb by multiplying by 10⁻�3. So you have 1.32 times 10⁻�3 coulomb divided by 60 voltage. So that will give you the answer in farad, because when you divide 1 coulomb by 1 voltage, give you 1 farad. Let me just mark it here in red. Coulomb per farad, coulomb per voltage is equal farad. This is the unit, right? So when you do the division of these two numbers, 1.32 times 10⁻�3, let me do it in the calculator and get you the result here. So using the calculator, we'll have 1.32 divided by 60 and 10⁻�3. I got this number, you know, it's a very small number. Oops, just a second. 1.32 divided by, I just want to write exactly what I got on the screen. I got 22 times 10⁻⁶ farad. That's the answer, okay? To convert this to microfarad, from farad to I multiply by 10⁻⁶. So we'll say it's equal to 22 times 10⁻⁶ times 10⁻⁶. That's I multiply y to change from farad to microfarad. So 10⁻⁶ and 10⁻⁶, they will cancel each other. So what's left? 22. That's how I got the answer. It's very important to know how you convert. All right. So that's the capacitor. All right. Let's say that, let's take another example. What about now? We know that let's say that you have a capacitor. You can make a capacitor look like that and connect it to a battery. Let's say that the capacitor, the C, is equal 470 microfarad, and the voltage is 40 voltage. So what the quantity of a charge will be accumulated across the capacitor plate? You know we know that C is equal Q over V. Now we want to find Q, so Q will be equal C times V. C is equal to 470 microfarad, and micro 10 negative 6. That will be farad. And the voltage is equal 40 voltage. So you should get in coulomb. So you multiply for 70, you get 18.8 times 10 negative 3 coulomb. Well, I can convert this to millicoulomb. How we convert to millicoulomb? To convert any unit to milli, you just multiply it by 10 power 3. So I'm going to multiply by 10 power 3. I'll say I have 18.8, 10 negative 3, and then I multiply the whole thing by 10 power 3 to make it millicoulomb. Again, 10 power 3 and negative 3 will cancel, so the answer will be equal to 18.8 millicoulomb, and that will be the answer. So we solved the two examples, how to find the capacitance and how to find the total charge, if you know. Okay. So let's move to something important, that how can you find the capacitance, how to calculate the capacitance, how to calculate the capacitance using the dimension of the capacitor. You have a capacitor and you want to use the geometry, the dimension, the length, the area, the thing like this. Well, so the capacitance, as you know, we have like two plates. They are parallel. Let me just try to make it nice here. So two plates, and they are from conducting material. Could be like a little bit thick. It's thin, you know, not just two. So these are the plates of the capacitor, and it has area. So it has area. We can find the area, and there is the separation distance between them. It's called D. All right. So that's D. Let's say measure in meter, and the C in farad. Well, and there is dielectric material. Dielectric material will be in the middle. Just let's make it like something in the middle here, between the two conductors. You fill the space by this material. Let's just so that's the dielectric material. Which is not conducting. It has coefficient called epsilon. What is epsilon called? Permittivity. And the unit farad per meter. A is the area of the plates, and it's measured in meter square. D is the distance between the two plates, or the separation distance. That's equal to That's also measured in meter. All right. E is constant. It depends on the material. When you ask about the permittivity, that's the constant of this material, and it depends on the material, whatever material that you have. If you don't have anything except air, so we give it the symbol E naught. So E naught is the permittivity of air or vacuum. Or vacuum. Nothing. You just leave it empty. It has, so but of course we have air, and that's constant number. We'll give you the number now. It's constant, small number, 8.85 times 10 negative 12 farad per meter. So that's the constant of the permittivity of air. What about if you have another material? If you have another material and you find its E, we always relate it to E naught. So it's equal to number multiply ER times E naught. E naught, we know permittivity of the air. What about ER? We call it relative permittivity. Relative permittivity. What does it mean? It tells you how many times it's bigger than the permittivity of the air. So maybe it's 10 times the permittivity of the air, or maybe it's 40 times, 100 times. So just ER is a number. It tells you the permittivity of this material, how much it's bigger than the one that we have. For example, let me just get the table, and I'm going to give you a table. Let's say that, but first we'll take one like paper, for example, or paper, yes. All right. This paper has ER equal to 2.5. So if you want to find E for paper, if you want to find the permittivity of paper, you are going to multiply ER times E naught. ER for paper is equal to, 2.5. 2.5. Multiplied by E naught. E naught is equal, it's a constant, 8.85 given there, 10 negative 12. And you find the result. That will give you the total epsilon of this one. Okay, so now we understand what does it mean every variable name. So I'll go back again. If you want to calculate the capacitance of a capacitor, you got to know three parameters: the area, the separation distance, and the permittivity. All right. And permittivity, what does it mean? It's a measure of how easily a material permits the establishment of an electric field in the material. Because why? Because you know that when you have a capacitor, and I think you have this in physics, and you have two plates, all right, and you connect these two plates to a battery or source, positive and negative. So there will be a positive charge on this plate connected to the positive and negative charge on the other plate. And in the plate, inside the plate, you will have electric field. And this is the electric field lines. The electric field lines, not all of them will be allowed to be established inside this capacitor, except if the material itself allows. So the material, it's different from 1 to 1. So for the air, 8.85 times 10 negative 12, this is the value of the permittivity of the air to allow the electric field. Okay, that's the meaning of the concept. But now, okay, we understand E, A, D. So now tell me, how can you find the capacitance? How we calculate the capacitance? Okay, the capacitance has a very simple equation. C is equal to E times A divided by D. That's the capacitance. Remember, the capacitance is just tell you it's how much can store, how much charge can store. Okay, remember that capacitance. Well, so that's to find the capacitance. You're going to use this equation epsilon AD. And don't forget, epsilon is equal epsilon naught times epsilon R. All right. If we have now, let's have example to calculate the capacitance of any material. You just choose example. Let's say that we have a capacitor, and that's the way to look. That's equal to, let's say, 2 millimeter, 4 millimeter, and the distance between them 0.1 millimeter. And the material in the middle, let's just add material in the middle here, the dielectric material. Let's say made of, I'll just look at the table, made of mica. All right, mica. Find the capacitance. So let's say find the capacitance. C is equal epsilon times A over D. First, I'll find the epsilon. Epsilon is equal epsilon R times epsilon naught. How you find epsilon R? I go for the table. I find that for mica, epsilon R is equal to 5. And I'm going to show you the table now. So that's ER is equal 5 times epsilon naught. Epsilon naught, it's constant number. I'm just, I don't remember it, but 8.85 times 10 negative 12. That's right. Yeah. That's epsilon. And I want to find the distance. The distance is separation distance between the two plates, as you see it here. This is separation distance 0.1 millimeter. You have to convert it to meter. 0.1 millimeter is equal 0.1 times 10 negative 3 meter. And the area, well, obviously the area is like a rectangle, and you to find the area, multiply 2 millimeter by 4 millimeter. You have to convert to meter, so you have 2 times 10 negative 3 meter times 4 10 negative 3 meter. When you multiply, you will have 8 times 10 negative 6, and the unit meter square. Found the area. Now I have all three parameters. Then I can find C. C will be equal to epsilon. That's epsilon. Let me multiply it in the calculator and get the result. It's 5 times 8.85 10 to the negative 12. That's equal to 4.425 times 10 negative 11. All right, that's epsilon. D, what a D, we have D.1, that will mean 10 negative 4 meter. And we have the area. Let's just mark them so you know. This is the area. This is the D separation distance. And that's the epsilon. Now will be direct substitution in the equation. C will be equal epsilon, which is equal 4.425 times 10 negative 11 times the area. Area is equal 8 times 10 negative 6. And the distance is 4.425 times 10 negative 11. I will just multiply it now with my calculator. Get it? 4.425 times I got this answer 8 times 10 negative 6 farad. Alright, and you know, to get to microfarad I multiply by 10 power 6, so I'll say it's equal 8 times 10 negative 6 farad, and then I multiply the whole thing by 10 power 6. You will cancel, so I have 8 microfarad, so the capacitance is equal 8 microfarad. Next. Alright, I want to elaborate more on this relationship of this capacitance. C is equal epsilon A over D. What does it mean? It means maybe epsilon is constant, and you can change if E is constant and D is constant. So if you have two things constant, E and D constant, and A is variable, so we'll find that C is proportional with the area. What does it mean? It means that the capacitance is directly proportional to the area. You increase the area, the capacitance increase. So you can say C2 over C1 equal A2 over A1. Maybe if you fix epsilon and area, you make it constant. So the only one variable is D. C is proportional with 1 over D. So the capacitance is inversely proportional with the separation distance. Means D gets smaller, C gets bigger. So we say C2 over C1, since inversely you flip them, D1 over D2. Now if the area and the distance are constant, so it depends on the C, it depends on E. So C2 and C1 equal E2 over E1. That's obviously from the relationship. Well, since we understand that, I'm going to give you interesting example to see how can you do that. All right. The first one, let's say that you have, I think I have, can I get you the sketch? Yeah. Yes. Now look at the problem A to find the C for the unknown. I will take the screenshot of this one. Now you have capacitance. This capacitance on to the left, the distance D, and to the right D, so it's the same. And the area is different. The one to the right is 3 times the area. Obviously, we want to find the capacitance of this one. We can find this capacitance relatively to the known one C. So I'll call this one and this 2. So I will say C1 is equal to 5 microfarad. I don't know C2, but the area 1 is equal A, and area 2 is equal, I see 3A. So now do you know 3A? Here you go, that's 3A, all right? D is the same, so D is constant and epsilon is constant. You have air, or you have ER here? The same, you see, the same D and ER. So D and E are the same. So we know that from the, if we write the relationship or the equation, C is equal epsilon times A divided by D. Obviously, these are constant, so C is proportional directly with A as explained last time. So you have C2 over C1 is equal A2 over A1, directly proportional. C2 is the unknown, C1 is equal 5 microfarad. equal A2 over A1. A2 is equal to 3A and A1 is equal A. So that will cancel, the A cancel with A, and then you cross multiply, then C2 will be equal 5 microfarad times 3. So you get 15 microfarad. So this capacitor has 15 microfarad. So that's how you solve using the relationship between both. Excellent. Okay. And I'll give you more exercise. Let me give me one more example. Let's just have another example. I'll take this one. Because you'll have homework, applying these things. Yeah. So now just C1, read the first one to the left is C1 is equal 1 point microfarad. C2, we don't know C2. Distance is different, so D1 is equal D, but D2 is equal 2D, right? What else? The area the same, so we'll look for the equation. C is equal epsilon AD. Obviously, that it tell you area is the same, cancel it. Epsilon the same, cancel. So you have 1 over D. So C is proportion with 1 over D. What does it mean? C2 over C1 equal what? D1 over D2. How you solve it? All right, C2 over C1 is equal 0.1 microfarad. Equal. D1 is equal D. D2 is equal to D. Now they will cancel. D cancel. So you find that C2 is equal 0.1 microfarad times half. Will be 0.05 microfarad. And you got it. That's the answer. See? So just find the relationship between them and you can continue to solve anything. Okay. How you calculate the electric field? We just explain how to find C. Let me just C is you can calculate it by this using equation, and also there is a relationship between Q and C, and the Q is equal CV. But I want now the electric field. The electric field that's inside the capacitor, it's equal to V over D. So what is that? That's electric field. Let's take one example how to calculate the electric field. Well, so this example will have everything in it. Let's say that you have capacitor consists of 2 plates, and connected by some wire to the rest of the circuit, and the length given in inch this time. I'm going to have different 2 inch and by 2 inch, like square. All right, and the distance very small, actually. Usually it's 1 over 32 inch, and it accumulate connected to voltage source equal to 48 voltage. All right, and of course you will have Q positive here and Q negative here, the bottom actually, not here, the outside. We just run. The question is, we need to find the capacitance. What is the capacitance? Well, since they don't mention anything, they don't show the electric material, it means that the electric material is air or vacuum. There's nothing between that. So I'm going to see your E is equal E naught, which is equal 8.85 times 10 negative 12. That's the epsilon that you're going to use. Okay. So what is the area? All right. That's tricky a little bit because you have to convert units. 2-inch, you got to convert it to meter. So how you convert it from inch to meter? All right, I'm going to show you something easy. You just multiply by 1 over 39.37. It will convert it to meter. All right, if I do that, so 2-inch will be very small, of course, in meter. That will be equal to 50.8 times 10 negative 3 meter. The other 2-inch will be the same thing, all right? So any 2-inch will be the same value. The distance D, 1 over 32. 1 over 32 inch. What's one? How to convert it to meter? We'll do the same thing. Let me write it in the correctly. 1 over 32. That's all inch, all right? You multiply by 1 over 39.37. Let me just do it. 1 over 39.37. 32. I got it here. But first I have to fix this is not 33, 32. That will be equal 793.8 times 10 power negative 6 meter. I got everything converted. That's the first thing. Convert from inch to meter. Now I'll find the area. The area is equal, that's square, so you should multiply 2 inch by 2 inch, but don't forget I'm going to use this. Just I will remind you, that's equal to 2 inch by 2 inch, which is in meter will be equal to 50.8 times 10 negative 3 times 50.8 times 10 negative 3. It will be in meter square. It will be in meter square. So let me get the answer like a question. 50.8 negative 3 and I got the answer to 0.58 times 10 negative 3 meter square. Okay, so that's the area in meter square. What about the distance? I got the distance already. That's the distance. So I plug the values. So what is the C? C is equal epsilon A divided by D. Epsilon, I have epsilon here. That's the value of epsilon. It's a vacuum. 8.85 times 10 negative 12 times the area. The area I just got it, 2.58 times 10 negative 3 divided by the distance, which is equal to 50.8 times 10 negative 3. I should get this in farad, and then let's just see what we got here. I got 28.8 times 10 negative, just a second. Oh, 10 negative 12. Oh, that's very small. So when you have something negative 12, you make it picofarad, not microfarad. Microfarad, remember, is negative 6. That's negative 12. So you multiply it by, if you want to make it pico, you multiply by 10 power 12. Will cancel, then you have 28.8 picofarad. So 1 picofarad is equal 10 negative 12 farad. Don't forget 1 microfarad is only 10 negative 6 farad. Okay, we're just learning time by time some unit. They are so important with capacitance because usually they are so small. So I solved the first part of the problem, which is similar to a previous example, but I'm just doing a long example a little bit. Now let's continue. We found the capacitance. What else? Find the electric field. The second question will find the electric field. How you find electric field? You remember the equation that we used just a few minutes ago? The electric field is equal voltage divided by distance. All right. The voltage was 48 volt you use, and the distance or the separation distance in it's 1/32 inches, and we convert it to meter. And what is the D? Yes, here is the D. 1/32, that's 793.8 times 10 negative 6 is the D. So I'm going to substitute the value of the distance, which is equal, how can I make it, well, if this is meter, 10 negative 6, 79, I can round it, 794, just 10 negative 6 meter. Okay, 794. 794 times 10 negative 6 meter. And doing that, I'll find that's equal to 60.5 times 10 power 3 and the unit voltage per meter, because I'm dividing voltage per meter. Tell me, how do you know that? That's the voltage, that's the meter, that's the unit. Well, since it's 10 power 3, I can replace it by kilovolt instead of so I'll say it's equal 60.5 kilovolt, because 10 power 3 here. Kilo. I remove it and I put kilo. So that will be the answer. That's the electric field. Let's find the charge. Find the charge. Total charge accumulated on the capacitor. Find the total charge accumulated on the plates of the capacitor, which is Q. Well, we know how we find Q is equal C times V. We got C before. That's the C. Pico, 28.8 picofarad, which will be 10 negative 12 farad. All right. The voltage, 48 voltage. I multiply to get that charge. I found really is very small. I find is equal to 1.38 times 10 negative 9 coulomb. So when you have negative 9, that's B nano. We remove it, you got 1.38 nano coulomb. So let's add to the list. 1 nano equal what? 10 negative 9. Nano what? Nano anything. Nano coulomb, nano volt, anything, any nano. So just 1 nano, let me just make it clear. 1 nano, 1 pico, 10 negative 12. 1 micro, 10 negative 6. Don't forget these units. So that's we found most of the variables that we need. All right. So I will just stop here and I will continue in another video for the capacitor. I will divide it into two, not to make it long. Okay. Thank you.